So, welcome again to this new lecture on solar photovoltaics principles, technologies and materials. So, we were discussing PN junction and light. We were not able to finish this analysis in the last lecture. So, we will try to finish this in this lecture. So, what we did in the last class, we will just recap first. So, in the last class what we did was we initiated a basic framework for determining IV characteristics in light. Okay. So, we had already done some analysis in dark. Quite a few of those conditions are still valid. So, basically what we did was you still consider this as a typical PN junction. We divided the device in 3 regions. One is region 1, that is quasi neutral region on P side. Then we divided this, we had region 2 which is the space charge region, that is the depletion region, and then we have region 3 which is the Q and R on N side, right. We assume that the device is in a steady state. So, basically we consider a fixed voltage or fixed intensity, and at a given time we have taken the depletion approximation as valid, and then we solve for basically carrier concentration and current from all the regions. So, from bulk region as well as now from the depletion region. See, the earlier in the depletion region, in dark no current was produced, I was equal to 0, which means whatever goes in goes out. But in light, this space charge region, you can say this is ISCR. In ISCR is not equal to 0 because of generation and recombination. Okay, because remember this region. So, although it is a depletion region, what did it mean? It is a depletion region. So, on this side you have on this side, if this is P, this is N, on this side you are going to have acceptor ions, on this side you have donor ions, all right. Now, it is depletion region because every free hole and free electron is cancelled out here, they have neutralized each other. As a result, there are only ionic cores, but still it still has a valence band and conduction band, right. So, electrons can still, so if you look at the energy band diagram, the energy band diagram is something like this, all right. So, which means in this region also however it is changing as a function of distance, however when you shine light on it, the electrons from this side can still go to this side and creating a hole. So, this region is still capable of producing. So, when you shine light, it will produce carriers. So, you can have carrier generation when you shine light, but when you generate carriers, then you also recombine carriers because generation and recombination are dynamic processes. So, because they are away from equilibrium condition, so excess carriers in valence band will always have tendency to return back to the valence band to minimize their energy. As a result, they will lead to recombination. Recombination can happen because of traps, it can happen because of radiative recombination, whatever the recombination mechanism is. Generation will always be accompanied with recombination, right. So, while generation will increase N and P, recombination will decrease N and P, and the combination of these two will give you net current. Okay. So, now depletion region produces current, and we will have to see what kind of current does it, how much current does it produce. So, that is what we were doing, and we also wrote the minority carrier equations. Which was basically 3 terms. First was the diffusion term, then you have recombination term, then you have generation term. All these 3 are equal to 0, and we now need to integrate these, we now need to analyze these equations. So, we will not go through the complete derivation of it, but we will just do a few things for this. So, first thing is we have to analyze what are the boundary conditions in order to solve the equations. So, boundary conditions are at the surface of P and N side. So, that is at x is equal to minus xp and x is equal to xn. So, that is if you take this as a junction, this is at x is equal to 0, this is Wn, this is minus Wp, this is minus xp and this is plus xn. So, this side is N side, this side is P side. Okay. So, at x is equal to minus xp, the surface, there is all, when you have a surface, the carriers go to the surface because of presence of dangling bonds, because of presence of other surface defects, there is surface recombination. So, at the surfaces of P and N side, the diffusive component dN del of delta n by dx, which is the diffusion current because of perturbation of charges, is equal to surface recombination, that is Sn into delta Np. This is the generation, this is the recombination term that we saw when we were talking about the recombination surface recombination term. So, at this, on the surface, basically you can say the diffusion current is limited by the surface recombination. So, the carriers which diffuse out, they get recombined at the surface. On the other side, at x is equal to xn, you have the other condition, that is minus dp del of delta Pn by dx, del x is equal to Sp into delta Pn. So, this is for, you can say this is for P side and this is for N side. So, first boundary condition is that diffusion term is equal to the surface recombination rate on the surface. And then we have the next term, that is at the junction of bulk P and N side with the depletion region, that is at this and this point, that is at x is equal to Wn and minus Wp. So, at x is equal to Wn, delta Pn is equal to Ni square by Nd into exponential of Qv by Kt minus 1, and delta Np is Ni square Na into exponential Qv by Kt minus 1. V is nothing but same as applied. So, V would be as we have seen is as we have got it from the other previous analysis in PN junction in dark. So, these conditions are similar to what we saw in dark. At the boundary, delta Pn is equal to Ni square by Nd exponential Qv by Kt minus 1, and at minus Wp, delta Np is equal to same Ni square by Na into exponential Qv by Kt minus 1. So, these are the boundary conditions at the surfaces of P and N side and at the junction of P and N sides with the depletion region. So, now when you apply these boundary conditions and solve the differential equation, I mean it's a little tedious differential, it's a little tedious solution, but it's not very difficult to do. You can do it yourself. In fact, I would recommend you to go do it yourself as well. So, if you do the solution, the general solution for NPEx and PNX works out to be like this. NPEx, that is minority carriers on P side. Okay. So, electrons on P side, their concentration as a function of energy and distance varies as An cos of hyperbolic minus x minus Wp divided by Ln plus Bn sin of hyperbolic minus x minus Wp by Ln plus gamma n exponential of minus alpha into x plus xp, where this term gamma n is alpha into 1 minus r in ln square divided by dn into alpha square ln square minus 1. Okay. You can see that we will see this later on little in detail, but let us first just go through the general forms, and then for P and x you get similarly for Pn as a function of energy and distance you have similar terms. So, Ap cos of hyperbolic, instead of minus x minus Wp by Ln, now we have x plus Wn. So, this is for electrons on holes, that as a result you have this minus Wp term appearing because this is on the P side. On the N side for the holes you will have Wn term coming, and since you are talking about holes, the minority carrier diffusion distance is considered. So, you have a cos term, you have a sine hyperbolic term, and similar term minus of, so instead of plus gamma n you have minus of gamma p exponential of minus alpha into x plus xp. Now, this again, so this gamma p is okay, that is all right, I think that is okay because it is coming from the So you assume that you have a junction like this, okay. So this is what P, this is what N, and the radiation comes like this, okay. So every carrier that has to reach N side has to go through P, okay. So some terms will remain similar because it has to still cover that distance. So again you have expression for gamma P, so you have an expression for gamma P which is alpha into 1 minus R IS LP square divided by dP into L. So you can see that the only differences that you have, you replace Wp by Wn, Ln by Lp, An by Ap, and the electron terms are basically replaced by the whole terms. So when you apply boundary conditions to these equations to find out the value of coefficients, we have this value for An, which is, so for the electrons, An is Np naught into exponential of Qv by Kt minus 1 minus gamma N exponential of minus alpha Xp minus Wp. Similarly, you have a term for Bn. It's a fairly complex looking term, but you have here is you have if you look at this carefully, you have a term which is dependent upon the bias, which is here, but you can see there are other terms where the bias doesn't come into picture. So there is only one term which is bias dependent. Similarly, here you have only one term which is bias dependent, and when you plug in the value of these An and Bn, so similarly you will get the values of Ap and Bp also when you apply boundary conditions. The currents, so let us leave it there right now, right. We know that we can calculate. So basically what you have done is you have just taken the solution of differential equation, the general solution, boundary conditions, calculate the value of coefficients for any differential equation. It's just that it's too complex to read out, but you can look at them from your notes as well as from the books, that these are fairly complex terms for An and Bn, but they are not that complex when you think of it. So we'll do that analysis in a little while. So we have An, Bn, Ap, Bp, and we know that the currents are due to diffusion only. So currents Jp is equal to minus Q dp dpn by dx, and Jn is equal to Q dn del np by del x, not dpn but del np by del x. These are partial equations. So when you now replace these expressions and calculate the current, so you don't have to worry about the complexity of the equation. What we have here is you get two terms for, so this is electron current at minus Wp and hole current at plus Wn, okay. So when we look at total current, hole current is calculated at plus Wn, electron current is calculated at minus Wp, and then we will do another current which is the SCR current that we will take at the end. So this term, which is the illumination dependent term, the first term you can see you have terms like Q, electronic charge, reflection coefficient, absorption coefficient, minority carrier diffusion length, all these are constants. This is the only term which is varying, that is Is the intensity of radiation. Everything else, so x is the distance in the device, Wp is also distance in the device for holes. So you can see all the terms, and Sn is the surface recombination velocity. So you can see that the only variable here is illumination. So this term, big term, is the illumination dependent term. The second term, which is a red one, has bias. Again, all other things are known. It is bias which varies. Similarly for holes you get the similar expressions. So what you have here is you have two terms in the current. One term is the illumination dependent term, second term is the bias dependent term, and these are two independent terms. They are not dependent. So the good thing is that if they were dependent, you would have a lot of difficult time, but since they are independent term, you can analyze both of them separately. So suppose what will happen in case of illumination is equal to 0. If illumination is equal to 0, then these two will become similar to what you calculated in dark, right? They will not be very different. So if you make Is equal to 0, if you just have this term and this term, it should give you the answers which are similar to what must have happened in dark condition. So essentially you can do that very easily, and similarly when you put the bias equal to 0, then what should happen? And then so another thing that you need to note is that the illumination term has this minus sign, whereas the bias term has a positive sign to it. So this tells that at zero bias solar cell is going to produce the current is going to be negative, alright. So when you plot the IV characteristics for a PN junction, the IV characteristics will not be like this. You should start at somewhere here. This is the illumination current, and then as you increase the bias, this current reduces and goes to 0 at certain point, at certain bias, and we will see what these terms are, and this is what basically the IV curve you should obtain for a solar cell when you plot this for a given illumination. Okay. So when you fix I, then you should obtain a IV curve like what you, so this would be dark, this would be light, and whatever is extra coming is because of illumination. So this shift from this side to that side is because of illumination effect. All right, and we are lucky to have these two terms independent of each other. They are not so that they are easy to analyze. And the meaning of this, you see, I just wanted to dwell a little bit upon this boundary condition. This boundary condition essentially is a realistic boundary condition because we are assuming that surface recombination is finite. Okay, and surface is basically within a few diffusion lengths of junction. So surface is not very far from the junction. Okay, if it happens that surface is very far from the junction, then basically you can say minority carrier concentration must be. So essentially you will have to change these boundary conditions when the surface is very far. But generally the solar cells are like this, that the surface recombination is finite in the solar cells. So this is a realistic boundary condition that you want to apply for solar cells. But you may have other boundary conditions if your solar cell junction is if solar cell device is very thick as compared to the depletion region. So when your device is very thick, then obviously or you can say that the width is much larger than LP or LN, then you will have to change the width of the device. Okay, device width, then boundary condition will change and hence your solution will also change. So this is for more realistic condition of having a device where, so as I said, the good thing about this expression is that it gives you two terms. One is the illumination dependent term, second is the bias dependent term. The illumination term is negative in nature, bias dependent term is positive in nature. So at 0 bias, whatever current you get is because of illumination. Okay, and as you increase the bias, the current reduces and it becomes 0 at certain bias when both of these terms cancel each other for both electron and hole currents. So this is what we obtain from this expression. Now we look at the, so what we have done is, we said earlier that J total was equal to J SCR plus Jn at minus Wp plus Jp at plus Wn. Okay. So instead of, because these two currents can be calculated from the diffusion equations quite easily, and this SCR current has to be, so now you will appreciate that why did we separate. So when I was explaining this particular point, anyway, so let me just so when I was saying that J total, so I said earlier that J total was equal to Jn at minus Wp plus Jp at minus Wp. It is easy to calculate this, but it is not easy to calculate this because carriers will immediately diffuse away. So so instead of doing this, you do Jn at minus Wp, which can be calculated easily using diffusion, using the solutions. Jp at Wn, this is also calculatable, and then whatever is generated from SCR region. So that is what we are going to look at now. Current which is going to, so let us look at the space charge region current between minus Wp and plus Wn. So the generation current in space charge region, J gen E we define as, is equal to minus of Q minus Wp plus, so first you look at the generation current, because space charge you will have generation as well as recombination. So generation current is basically integration of Gex dx over minus Wn2 plus Wp, and this turns out to be like this. So we know the expression for Gex, so you plug in there, you get this term Qis 1 minus r exponential of minus alpha xp minus Wp into 1 minus e to the power minus alpha p into Wp plus Wn. Now you look at the recombination current. When you look at the recombination current is, so we assume that it's Shockley-Reed Hall trap assisted recombination dominates via trap states. So this is SRH means Shockley-Reed Hall. Okay, this is basically for trap assisted recombination. So we are not assuming a radiative recombination, we are saying it's a non-radiative trap assisted recombination. Then J recombination is Q minus Wp to Wn R of dx, right. So of course this current is negative in nature and this current is positive in nature, because generation current is produced, you create electrons, and recombination current means you consume electrons. So both have opposite signs. So now you put in the R of recombination rate for Shockley-Reed Hall mechanism. The recombination rate is given by this expression that we wrote earlier also, R is equal to Np minus Ni square divided by tau n into P plus Pt plus tau P n plus Nt. This is the expression where Np is the carried electron and hole concentration, Ni is the intrinsic carrier concentration, tau n is the lifetime of electron, Pt is the hole trap density, and Nt is the electron trap density. So when you do this analysis, so this integration turns out to be in this fashion. So you have Qni Wn plus Wp divided by square root of tau n tau p into 2 of sine of hyperbolic Qb by 2 kt divided by Qvbi minus p divided by kt into some term eta. Okay, this is approximately pi by 2 if you have forward bias which is sufficiently large in nature, whereas here Nt and Pt are carrier densities when respective Fermi levels are equal to trap levels. Okay, so they are basically carrier densities corresponding to when Fermi levels are equal to trap levels. So they are not actually trap densities, they are carrier densities. So Nt is again it is a similar expression, Nt is equal to Ni exponential Et minus Ei divided by Kt, and this is Ei minus Et by Kt. So similar to electron and hole concentration in an N type semiconductor, you calculate the N electron hole concentration with respect to trap. So now this generation current, that the total SCR current now is, you have to now integrate. So total of course we have taken the spectral response for each energy, you have to integrate these. So this generation current, this J gen, so if you have to now look at J total gen, you have to integrate, right, Eg to infinity J gen E dE, right. So this has to be integrated. So that is why I have written in the next slide that J gen E is integration of this small j gen E over all energies. Then the total current that you get is essentially this recombination current, this is the recombination, and this is the generation. Okay, and you can see that it has certain bias dependence here, and you have again these two terms are decoupled. You have a term which is bias dependent, you have a term which is illumination dependent, but these are finite terms, they are not zero unlike it was in dark. Okay, so now this J total of a p-n junction device in light that we have calculated is minus J n at minus Wp plus Jp at plus Wn plus J SCR. This is the total current that you will get out of a solar cell device p-n junction in light condition. All right. So we will now, we have done a p-n junction analysis for dark as well as light conditions, which gives you a fair idea of how to get these expressions. And this current, as we will see, will be called as photocurrent or short circuit current for a solar cell device. We will see later on. So, we will do now solar cells in detail in the next class onwards. Okay. Thank you.